imagine I have a bar over here, alright, and then you place it in a uni-tensile forces, so you're trying to stretch it. So when you stretch it, it somewhat move in a certain changes of distance. Alright, we can analyze things in terms of a so-called the elements method, the finite elements method. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We can break down into 5 elements, and we just take in these elements. Let's just zoom in this element over here. Okay, we call this element 5. So you have a force over here. Alright, this is the very force over here, which is very large. So stat likewise, this at this point, the forces over here is also super large. And as you go further downwards, alright, at this point, alright, this is somewhat a experiences lesser tensile force, because you're much further away from the concentrated force over here and here, right? So never mind, later on we'll tap into this understanding. So therefore, I'll just let you know that the further you are away from the concentrated force, this means that you're experiencing lesser tensile force. That's the meaning. Alright, so if you were to apply certain force over here, alright, you have a certain reaction force over here at this side, alright, because the element force material is trying to resist it. So I'm trying to so-called prevent it from pulling apart, because this is one beam or one bar. Right, this whole bar is a solid bar, so therefore within itself there is a molecular systems to prevent it from distortion. Not distortion, but rather than being break off or things like that. So there will be a reaction force over here. Alright, but however, this reaction force comparatively to these forces that is acting on this concentrated force over here is so large that it actually overruns these forces. Right, so we will have a much larger force over here. So you are pulling at a much larger force than the element 4 trying to restrain this pulling, because at element 4, this, as we say, we are further away from this concentrated force, and therefore at this point you are actually having a lesser force, much lesser force compared to here. Alright, and therefore this much lesser reaction force cannot tahan this super big force over here. I hope that this is pretty clear for you, and therefore in such of a case we can erase this thing because it's negligible comparatively to the force over here. And this is why you in a lot of diagrams you often see these directions. This is the meaning of that. The next thing I just want to convey is that within this particular element 5, we can actually break down into two different stuff. We can call this F2, alright, the force acting on this point, and the force at F1. Alright, let's leave it as F1 and F2. Within themselves, as we know that within themselves they also have their own internal forces, because it's trying to prevent any molecular breakdown. So they are trying to resist the system. So it's talking about the constitutive system within itself, the material and things like that. Alright, but nonetheless, there will be a much larger force over here also, that knowing that we will have a small force something over here, but it's negligible, because this forces that is pulling is so much further away, because this point is so much further away from here. So the magnitude of here comparatively is somewhat negligible. Okay, I hope that this is pretty clear for you to understand. And therefore, with all these things, alright, let's just go into some diagrams. So I'll not go into details of whether is this my element or whether is this my original element. After I stretch it, it becomes like this. I'll not go into details of this because this diagram I don't understand much. But I just want to convey to you that the strain, the changes with, let's say you pull this particular element, we call this element 5 just now, right? When you pull this thing over here, there may be some stretching, alright, and there may be also some stretching over here because of other elements trying to resist, alright, trying to resist the pulling, just to let you know. So therefore there'll be some changes and some changes over here, alright, therefore there's some changes of L, some changes of L. So if you add up all together, the changes is simply U2 minus U1. Alright, that's why I tell you that something, some understandings I may not understand. Where u2 minus u1, as you know, u2 is over here, u1 is this one. He's talking about this distance over here. So it's like in between. I don't know what the hell is going on, but anyway, let's just take the understandings and just plug it in. Alright, so we have we say that the changes is u2 minus u1. Alright, and we know that strain is the changes, the little changes over its original length. Alright, therefore you just write it over here, where your E is equals to u2 minus u1. Alright, then after you can do the Hooke's law, the constitutive equation of the material, and therefore just simply sub in your strain over here, where is E over L, while your where you can expand your E into this form, your Young modulus, you would say. Okay, hopefully it's pretty clear. Wait, sorry. This E is this E, alright, where E, this capital E is your Young modulus. Okay, sorry, my fault. Alright, so I hope that this is pretty clear. This is kind of straightforward. Then the forces, you know, is stress times area. So just simply, because since you know your stress can be re-represented in terms of this, you just sub in it also. So you'll have E over L, u2 minus u1. Okay, where this force internal tells you the within the solid itself there may be some molecular breakdown or things like that. So the internal system will have a certain internal forces, things like that, heat everything. Alright, so nonetheless we see that the K is equals to A over L. Okay, and in the later part of the videos we'll rigorously talking about this K equals to A over L, the strong form and the weak form. But before I go into introducing this thing, I'll just continue finishing how we get the F equals to KU. Alright, because you see force 1 over here plus the force internal, which is force 1, add up with force internal because they are in the same direction, ensure that for equilibrium system it is equals to 0. Why is that so? Is because this force, as you know, is pretty much somewhat pretty much equals to this reaction force, where am I? Yeah, to this reaction force over here. Okay, and therefore since this is okay, I'll not go. Okay, never mind. I will not go into details on how we define this. Okay, because the understanding is very abstract. Alright, just take note that this thing over here is simply this equation if you take equilibrium of it. Although they are going in the same direction, or they should be equals to 0. Right, because in some extent, in a more complicated way, because this element itself is just within a bigger system, because there is 5 elements, right? So then this 5th element, we are breaking down it again into this piece and this piece over here. Alright, and therefore, yeah, as you know, things got a little more complicated, but just leave it as this is the equilibrium system, while this one is the equilibrium system for this one. Okay, where your F2 is in this direction and your force internal is acting against because it's going in this direction, so therefore it's minus. Okay, you rearrange this thing, and then we know that force is equals to K u2 minus u1. This is what we have learned just now. Alright, this equation. So just simply sub in the same equation back to our forces. Alright, where F1 and F2 can be re-represented in terms of this thing. Okay, you rearrange, you should get this thing over here. Alright, because you put this all into matrix, you'll get this. That's all I want to say. You may ask me why is this negative? Because F1 is equals to minus F internal, because this is equilibrium, so you bring the F internal this side, the other side. So therefore the F internal is simply your KU2 minus U1. Alright, where this is minus F internal. Okay, so far so good. And then F2 minus F internal is equals to 0, so therefore this thing gonna move to the other side. So F2 is equals to F internal, where F internal we have shown you that is KU2 minus U1. Okay, so therefore you rearrange, you put in the matrix, you have your force is equals to K matrix times your UI. Alright, or your K is equals to EA over L. Alright, but nonetheless, if you factorize out the K out, you'll have EA over L, and then you have a series of 1 minus 1 minus 1, 1. Okay, so this whole thing is just a 2 times 2 system for your stiffness matrix. So if it's a 3 times 3, you will have other stuff. I don't go into details, but let's just keep it to this. So therefore we have introduced you how this E over L is somewhat important. Alright? Everything is very dependent on when you apply a tensile force, when you're trying to stretch a certain system. Alright? So within this thing, let's introduce you with what we're gonna do. Alright, this is somewhat of introduction for us. Okay, is that the EA over L, if it's a strong form, is this form. Okay, we'll deal with it in the later video, in the next video I would say. While the weak form is dealing with other stuff. We call it the weighted residual method, when it somewhat requires interactions between the displacement interpolations and geometric shape. So everything all goes into here. These are all calls. When you mix everything all together, you have a Galerkin's method. Alright, but I'll not go into that first. I just want to introduce you with this concept. And therefore the strong form, we are gonna talk about it in the next video, just to show you why is it a strong form. Therefore I shall see you there.